In this segment, let's look at how to define functions over recursive algebraic types. In particular, we'll look at the example of binary trees, and also we'll look at the example of lists. So we have a data type of trees. Remember, tree is either empty or it's a node with two subtrees and an integer component. We can use pattern matching over these to give us definitions of a function like isEmpty. IsEmpty takes a tree and returns true or false depending on whether it's empty. So isEmpty applied to empty is true, isEmpty applied to a node where we don't care what the values the nodes holds is. So we use pattern matching over wildcards there. The answer is false in that case. Similarly, we can define a function root that takes a tree and gives us the value that occurs at the root. Now, if we apply this function to empty, there isn't a value, so we call the error function with the string no root. If there is a value, if it's a node and the value held there is n, we just return the value n. And again, we use wildcards to match over the two subtrees because they're not relevant here. Now, what about defining recursive functions on a tree? Suppose we want to count how many nodes there are in a tree, and we call that the size function. So if we apply size to empty, we'll get the answer 0. There are no nodes there. If we apply size to a node with a subtree, a left subtree S and a right subtree T, well, what do? How many nodes are there? We count 1 for this node itself, and then we must count the nodes in S, so that's the size S, and the nodes in T. So we have 1 for this node, size plus size S for the nodes on the left subtree, and size T for the nodes in the right. So that gives us a typical application of recursion. We define the empty case outright, and we define the case for the node using the results for the corresponding subtrees S and T. Here's another function, another example. This is a function that takes a tree and flattens it out into a list of integers. So if we have an empty tree, then that turns into an empty list. If we have a node with left subtree S, value n, and right subtree t, what do? We form a list of the things from S, then we stick the element n, and then we have the list of things from subtree t. And you can see there that in defining list applied to node, we've used recursively both the value on the left and the value on the right, as well as the value n. Now, suppose we had to define the sum of a tree. There we'd be doing something similar, except we would take account of the values held at the nodes. So as an exercise, why not think about how to do that? And in the case of the node, you would expect to use sum of t on the two subtrees and also the value n. So that gives us a range of functions over trees. We can also think of lists as a data type. If you remember, a list is either an empty list, which we write open parenthesis, close square parenthesis, or a cons node written by saying a value colon or cons a list, the head colon the tail. Now we can write a type that's identical to that using a data type. We're saying list A here, so list is defined over any type A, and the elements are the empty list and then cons of A, a value, and list of A, a list. So that's constructed in exactly the same way that ordinary lists are. And so again, as an exercise, you can convert from a list of A to a built-in list of A and vice versa. The function toList will do recursion over a built-in list of A. The function fromList will do recursion on the list A type that we have defined. So you get examples of two different kinds of recursion. They're in fact the same because the types are the same, more or less.